So am I audible, guys? Can you confirm? Yeah, sorry, I muted. Guess I'm audible. Okay, fine. Thank you. So maybe we'll wait for a couple more minutes. Let's see who are all going to join this class. And by the way, so have you attended previous sessions or is this your first class? Whoever, Mr. Raj Mehta or Ravi Kumar or Nivedita?
Sir, I had joined before,
Okay.
but what had happened was I lost the connection, and once I was traveling, and I think Prabir Kumar Saha took class. And this class I didn't know last week because I
Okay.
had not got the message. Then I think because of some internet issues, I got it a little late.
Okay, ma'am. See, actually, these classes are happening since 6 weeks. This
Right,
is the
right.
seventh
That is
week.
what
Yeah.
I just checked for the message also, but I have
Okay.
not received any message. But by the time I think later in the evening I saw I had got the message and it was already 6:55 and I joined
Oh,
by
okay.
then.
Okay, fine, fine.
I was late. I was a little late.
Okay, fine. Okay. So, are you the ma'am? Are you the one who are asking question towards installation regarding?
Yes, sir. I'm not able to install
Okay,
it.
yeah, got
I
it.
am just attending my assignments just like that. I'm trying to, and I want to actually take up the exam, but since I have not installed now, also I am unable to yet install it because I don't know. I'm not. It is showing the license issue.
Okay, it is the license issue. Okay.
I have filled the Google form immediately as soon as I have downloaded the lesson from the links, whatever has been shared by the NPTEL team only. I have downloaded the lesson software and I tried to install it, but it is showing the issue of license.
Okay. Could you mail professor regarding this, the license issue?
Professor, I have not mailed. Can you give me his mail ID?
It's there in the course website, right? Isn't it? It's not there.
Okay,
I'll have
okay.
to check
I'll
it.
just check.
Yeah,
I'll check. I'll
yeah.
check, sir.
Please check it.
I'll check it.
Yeah. And there's one message which says, yeah, Ravi Kumar. So this is the first time he's joining. Mr. Raj Mehta, how about you? After due to timing issue, okay, you're unable to join. So among three, Nivedita ma'am, you don't have Aspen as of now. The other two, do you have Aspen with you? Can we do a hands-on experience session? See, unless you start working on Aspen, you really don't know where you're getting stuck, right? So, uh, if I go on talking the entire lecture, it doesn't make any sense because there's a live interactive session where it's parallelly we solve problems and I will help you out wherever you're getting stuck. So, other two, do you have Aspen with you now? Ma'am, if you don't mind, can you just mute yourself?
Oh, sorry, sir.
Okay, fine. Uh, So, before just going to the lecture, do you have any topic which you want me to discuss with respect to Aspen? Anyone? Do you have any specific thing which you want me to discuss? Any response? I see if you don't respond, I'll by default I'll assume that everything is clear with and you are able to solve all the assignments fine. That's all right. Yes. So I just do what I had planned. So yes, so I welcome you for the seventh lecture of this interactive sessions. So it will be good if you have Aspen with you now and you are able to do it. Okay. I actually plan to take up some example where we stopped last week. the air separation plant. Okay, thought of continuing it, but in case if you don't have it as of now, what I'll do is I'll just show you the procedure. Anyways, this is getting recorded, so later on as well you can try it out. Okay. So assignment problem, someone says, when is the due date for assignment 2 or assignment 7? Assignment 7. Because I haven't actually seen these assignments. Tomorrow, right? So in that case, I'm not allowed to discuss. Okay, so I can discuss it the coming week. So you have trouble in solving those questions, or the question itself is wrong? What was the issue? Some hints. See, I didn't look at the questions. I'll see towards the end of this lecture. I'll just go through it. Okay, because I actually didn't see the question. So we'll see. We'll work on it towards the end. Okay, fine. So what professor was discussing in this week is basically he took 3 different problems. Okay, so he tried to show you how do we simulate, set up the flow sheet, how do we identify the variables. So essentially in some of the cases, it happens that we know input of all the components. In however, in generally, when you are when you have a role of process designer, what input you have is what is the required quantity from the process, right? So let's say for example, if I'm talking of the same process, air separation plant, I'll say I want 1 ton of liquid nitrogen per day. Let's just assume. Okay, so the output is specified. Okay, now for the given output we need to design the required input conditions or flow rates, operating conditions, everything else. So although in most of the cases the inputs are available, those textbook problems which we solve, but in real life we are only given the outputs. Okay, so professor he started one way, right? So basically he gave all the inputs and asked you to calculate output, and in some cases he used the concept of design spec and sensitivity analysis to find out how the output variables vary as a function of input variables. So that's what professor tried to explain in the 3 cases. So one he says separation of hydrocarbon mixture, and then acetaldehyde, preparation of acetaldehyde from ethanol, and then it's another distillation process. Okay, so that's what the professor has been discussing this week. So what I had planned was, I'll just have very few questions. Okay, these questions will give me a message that you are going through lectures, and you are able to follow the lectures and all. Okay, so I have one question. So one of the concept which professor discussed is based on membrane separation. Okay, so I want you to answer if the Aspen Plus has a inbuilt module for solving membrane separation process. Is it true or false? I have a poll for this. Just give me a minute. Ma'am, just a second. I have a poll for this. Okay, just give me. If you answer on a poll, then I'll have some quantitative comparison that how many of you are able to follow. That's the only reason I asked you to wait. Okay, nothing offensive. It becomes easier for me. Can you answer on the poll? Okay, before actually asking this question, how many of you have used Aspen? Can you just put a text that you have used and using it often? Yes, someone is raising their hand. You can just put it on the chat box, whatever you have the issue. Okay, Mr. Raj, you are using else. So you are clear about the model pellets available in Aspen, right? Okay, thanks for your response. Others? Yes, okay. Okay, so only two of you, three out of six, only three of you are using, is it? Okay, see, I'll just give you some brief introduction. Okay, see, for the people who have not seen the Aspen Geo and all, see, when you go to the simulation aspect, you'll be able to see the model pellets over here. Okay, so it can give, it can simulate mixtures, separators, where you can see over here, right? So separators, you'll have phase separator, two phase separator, three phase separator, and a decanter based on density separation and separation, right? Then heat exchangers, various kinds of heat exchangers. One is shell and tube heat exchanger, which can carry only two streams. The heat exchanger which can carry only two streams is called heat ex, and the heat exchanger which can carry multi-stream, basically more than one hot stream or more than one cold stream. Okay, if you have in such system, that's called multi-stream heat exchanger, NHX. Then you have separation columns over here. Okay, so these two are based on shortcut methods, which we'll just see in this lecture, and RADFRAC is based on detailed analysis of distillation. Okay, then extraction, multi fraction. Okay, so for petroleum refinery we have a separate distillation thing. Okay, so it also has seven kinds of reactors, which are two of them are based on stoichiometry, two of them are based on Gibbs energy minimization, and three of them are based on kinetics. Okay, then we have pressure changers, which are pumps, compressors, valves, multi-stage compression system, etc., and pipes. Okay, then these are control variables. Okay, then you have pellets for solids handling as well. Okay, and separators, and then batch modules, etc. Although it has got tens of modules, it doesn't have a membrane separator. Okay, so what do? Is we take a separator which is available over here. For example, in this case, what I did was I just gave this flow sheet. You are able to see this flow sheet, right? So I have stream 1 where I'm expanding it and then sending it to a separator, right? So I'll say let me see what is the stream composition which I gave. So stream is 1. So I have a 3 component mixture, for example, methane, ethane, propane. Now I want to separate this mixture using membrane separation. Okay, so what this pellet does is it just gives a physical separation. See, you're able to see, given the outlet stream S4, this particular unit has three outlet streams, right? S3, S4, and S5. So when you go to this model pellet, we can actually give what fraction of the initial quantity we want to have in this particular stream. So in S4 I want ethane to be 1. Okay, and in S3 I want methane to be 1. In S5 it doesn't require any other input, right? Because it's the number of degrees of freedom available when the system is satisfied. So hence there is no need for giving this thing. So since I have only three streams, so two inputs will be sufficient. The other one will automatically get calculated based on mass balance, right? So although Aspen has got tens of modules, but it doesn't have absorption thing. Okay, membrane separation, not absorption, sorry, membrane separation model pellet, right? Yes. So the answer is false. So we are just physically giving it the separation process and assuming that there exists a membrane which will give us that output. Okay, so it's all physically done. However, there is no mathematical model at the back of Aspen which can solve this membrane separation process. Okay, fine. So I have another question. So whoever have Aspen with you as of now, I hope you should be able to answer this question. And yes, by the way, I'm asking once again. So do you have Aspen? Does any one of you have Aspen with you now? Maybe one at least. Okay, so okay, I can see some of you. Wow, that's great. Okay, then in that case, can you just open the Aspen file and give me an answer for this? So this gives you an idea of how do we calculate boiling point of pure components. Okay, can you just open Aspen and answer this question based on boiling point, basically volatility, right? So I'm asking boiling point is available. cannot run this pro. Why? Okay. Connected system with different servers, so I can't. Anyone else have Aspen with you? Only Mr. Ravi Kumar has it. Anyways, I'll show you how to we do it, but if you do with your hand, then it's far better. So others don't have Aspen with, is it? Akshay has just joined. Akshay might have. Akshay, do you have Aspen with you? No? Yes, that's great. Okay, then I have a question for you, Akshay. So I'm just projecting on the screen. So can you arrange these three components based on volatility? So Mr. Ravi Kumar, you have license issue, is it? Is that your problem or anything else? What does it say? With different server login. No, actually I didn't get what is the issue. So it what does the error show on the screen? What is the error which is coming out? Yes, madam. For this question, no, we need first. The first step is we need to find out boiling points at 1 atmosphere, and based on the boiling points, we need to arrange it. That's the basic idea. So the idea of giving this question is for learners to know how do we calculate boiling points at different pressures for pure components as well as for mixtures. Okay, I'll just explain how do we do that. But meanwhile, if the learners can, if you people can give me a response, that will be really good, because that's the aim of this class, right? So Akshay, I'm hoping that you're working on this problem, right? Okay, great. Thanks for the response. I'll wait for one more minute. After that, I'll just press it, because I can't keep others waiting for me, right? Okay, fine. I'll just show you how do we do this. See, once after we define, the first step what we do is to give the components, right? So see, in this already I gave the components, benzene, toluene, cyanide, right? So after that we specify the method which we are using. Okay. it can be any method as well. Okay, for as of now I'm using this NRTLRK. Okay, but it can be any other method as well, because it's just a prediction, right? So now the next step is, on the right side top you are able, you can see, right, the pure component, binary, mixture, solubility, PT envelope, and etc. So if we have pure components, let's try with pure, right, since we have only one component. Now what do we want to measure? In this case we were looking for dew point, right? So if someone is interested in finding density or volume, etc., whatever, so you can just see, you should be able to read the properties. Okay, once you put your cursor on the symbol which Aspen is using, you can read what it means. For example, this case, mass density of a pure component, similarly as entropy exponent of pure component, mass enthalpy, okay, ideal gas enthalpy, etc., so and so. So from this we will be able to calculate properties of different things. However, now we are interested in finding out the boiling point, right? Boiling point at 1 atmosphere. So I'll show you another method. So let me just delete this pure analysis I have shown you, because in case if you want to find out other properties such as whatever I have described, so it will be useful. Just go to analysis, click on new. It's generic, right? Generic. So now it says I want only one. So essentially by giving mole flow of 1 for benzene makes it as a pure component, right? So I want it at 1 bar. Can you, I don't know who has unmuted, can you just mute yourself if you don't mind? Okay. So we'll vary temperature. Okay, this is just a dummy calculation. Okay, I'll say I want it 20 tick CSSI, right? So let me put 150 is also 300. Okay, then what do I want to tabulate? It's the bubble point or dew point. For pure components it's the same, right? Doesn't really matter, bubble point and dew point are the same. So let me just run this analysis. Yeah, see, here we can see that at 1 bar it has got a dew point of 352 Kelvin. So similarly we will be able to identify dew point for others as well. So if I'll just remove this, I'll put tolvin. If I run this, now see at 1 bar I have a dew point of 382 Kelvin for tolvin, and similarly for other component as well. Let me delete the other, then run it. See, I have third one as 411 Kelvin, right? So now I have 3 component boiling points, right? So since I know boiling points, I should be able to arrange them based on the volatility. And another way of doing is just generate this PT envelope. Okay, and say I want to generate PT envelope. I want only this one. I would prefer using density matching method. You know, uh, since it's from our own lab, so I know what is going on with density matching method, so I prefer using density matching method. Okay, so once you see the results, so it gives you dew point at different not dew point, since it's a pure component, it says saturation temperature at various pressures. So since we are wanting at 1 bar, we will be able to identify that it's at 1 atmosphere, so we'll be able to identify that it's 353 Kelvin. Okay, so this is another way of doing. So could you follow what I did for finding boiling point or dew point? In case if you are considering a mixture, for example, in this case, if I want to have a mixture of 0.3 and let's say 0.4, and I want to know bubble point and dew point as well, that will be different, right? Obviously for a mixture it will be different. See, the bubble point and dew point for the mixtures on the same. For the pure components, both are same. Okay, so this is how you find bubble point and dew point for a pure component or for a mixture. Okay, for in case of pure component, it's called boiling point. In case of mixture, we call them separately as bubble point and dew point. So, is this clear? How do we find out the boiling points of different components and mixtures? Yes, any other responses? Thanks, Mr. Raj, for your response. For others, is it clear? Yes, okay, great. Ma'am, what did you miss in the first question? I didn't understand. First question, you say this one, right? So basically, there is no module in Aspen for membrane suppression module. Okay, so all we do is we physically give the values and assume that there is some membrane somewhere which can be used in this system to get our output. That's the only point which I made in that question. Okay, fine. Let me just continue. Okay, now this is one more question. So Fensky equation is the one which is used to calculate minimum number of stages required in the module, DM, whatever module I have shown you. So is it true or false? Just put a code for this. Give me a second. Yes. See, today actually I had planned for calculator box and optimization tools. Based on time, we'll see whether we'll be able to start those or we'll have to take up the next class as well. Yeah, fine. Just let me go to Aspen. So yes, when you go to the simulation section of Aspen, when you go to columns, you'll be able to see various kinds of columns over here. Okay, the first two are based on shortcut modeling basically. So for the given input and output, it will calculate us what are the minimum number of trays that is required, minimum number of minimum reflex ratio that is required for the system. All these things are calculated in the physical things. However, in the case of red frac, all these design aspects are needed to be given as input. Okay, so yes, the question whatever I have asked is true that it calculates minimum number of stages required for separation based on Fensky equation. Okay, okay, so I have one more question. So no, Akshay, you have Aspen with you, right? Can you just answer this? Go to the petroleum chemical relevant things in the method, and can you answer what all modules available, what all the property methods available inside that, or if any other candidate also has Aspen, they can also just look into it and answer this question. Others, obviously, I don't expect you to remember everything, and it's unfair, right? So, whoever have Aspen, please do answer this question. Is it Wilson? Don't you see any other property method? Option B. Okay. Any others? So the aim of asking this question is not for you to just go and look. The basic idea to show or to ask this question is for you to know that property methods, whatever property method we are using is just a prediction of the experimental thing. Okay, so it's just a prediction, and every prediction will have some amount of deviation. Okay, among all the models which are proposed in the literature, the models which are able to predict really good for petrochemical things are these ones. Okay, so that's the reason they have specifically put these under petrochemical property evaluations. Okay, so if you just go on if you just point your pointer to on the method which they have shown here, you will be able to see what things, what some more, what in depth it uses. Okay, if you want to read some more details of it, you can just go to help of Aspen, and there you will be able to find out what the method is actually using and all. Okay, so yes, so the aim of this question is for you to know that everything you'll be able to see over here. Okay, see, if I want to use something else, I'll say RK something. Okay, that's all. Okay, see, under this I was able to get both right, this one as well as Wilson as well. Yes, I have to, that's the answer. Okay, fine. So this is one more question. This particular figure corresponds to which model pellet in Aspen? Can you please respond? The figure, whatever I'm showing you, corresponds to which model pellet? Okay, thanks for the response. You are correct, it's actually the flash too. Okay, so if you go here, if you just pull it down, you'll be able to see that what is this? Under the flash, what input it is asking is exactly same information what we give for the flash calculation option. Okay, so that's what it is. Fine, thanks for the responses. Okay, so yeah, so this is where we stopped last class, right? So we said we're going to simulate the entire flow sheet. However, we just started with the cold section of the process. So what I planned for today's class is we'll simulate the heat exchanger part. Okay, the heat exchanger and the expander part. Okay, that's what I had thought of doing today. So yes, Akshay, could you finish this assignment what we started last week? You were present in the last class, right? I think you're the only one who have attended 2 days in the previous session as well. Could you finish this one? Or at least you understood the way which we are proceeding, right? That's also fine. Could you follow this? For others who have come just today, I'll just explain what we were doing. See, the aim of the overall assignment is to simulate the air separation plant. Okay, so it has so we said let us divide the entire plant into 3 sections and we'll simulate them separately. So one we have cold end, and one we have heat exchanger section, and one we have a double column separation setup. Okay, so last class what I was doing, I was trying to simulate this cold turbine. Okay, so the liquid yield, which is defined as ratio of nitrogen that is coming through the turbine, sorry, whatever it is getting liquefied to whatever it is being expanded. So basically it's m7 by m5. Okay, in this figure. So I wanted candidates to find out the temperature of T5 for various pressures such that I have yield of 0.6 and 0.7 etc. Given the outlet pressure of turbine is 6 bar, sorry, state 6 is 1 bar. Okay, so one I said using sensitivity analysis and another one I said using design spec. Okay, I'll just show you how we proceeded to this. So let me just make faster. Where are these pressure changes? Yes. So for air, I would prefer choosing Peng-Robinson equation of state. That's a good prediction. That predicts really great. Yes, it's Peng-Robinson. Pressure changes. Right, then I have a separator. Then some inlet, outlet over here. Let me take some 40 bar just as an example. Okay, I'll make it 40 bar. It's 1 kilo more, and I don't have nitrogen, so I'll have to add it. Great. So this is one. Okay, you're facing issue with sensitivity analysis. Okay, let us see. Actually, you'll get errors while you are performing sensitivity analysis. The question is framed, so the objective over there was for you to learn how to handle the errors. So the question was made such that you will get errors. So it says isentropic efficiency of 70%. Since the question says the output pressure is 1 bar and isentropic efficiency of 70%, you can see here, right? The output pressure is 1 bar given over here, and the isentropic efficiency of turbine is 70%. So that's what I gave, and I'm using Peng-Robinson equation of state. And since it's a two-phase expansion, so I went through convergence and changed the valid phases to vapor and liquid. Although the initial setup is it says vapor only, I'm changing it to vapor and liquid. That's the only change which I made. Okay. So with respect to flash separator, I'll say the heat duty to the flash separator is 0, and pressure drop is also assumed to be 0. Okay, let me just rename this and rename this as 5. I'll try using the same nomenclature. 6, 7, 8. Okay, so that's the setup which we have, and then I asked you to perform a sensitivity analysis, right? So how do we perform sensitivity analysis? You'll be able to see this model analysis tool over here. Okay, just go to that sensitivity, that's all. Go click new one. So here I want to vary my inlet temperature. So it's a stream variable, right? So I'm varying inlet stream temperature. So it's stream variable. The stream which I want to vary is 5, and I want to vary temperature. So let me start from 90 to 150, increment of 1 Kelvin. Okay, and I'll define since my inlet flow rate is 1 kilomole per second, so the denominator of this expression is already 1, right? So I'll say I want to find out outlet flow rate, so that would be sufficient. So this is M7. So stream, which stream, this is a stream variable since we are talking of the stream flow rate, stream 7, and I want mole flow. That's all. Variables. So let us see how does the liquid flow rate varies with respect to temperature. Let me plot it. So yes, here we are able to see that for 40 bar, as we decrease the inlet pressure of cryoturbine, obviously this is an obvious thing that the yield which we get from the expansion will obviously increase, right? So this is what I was asking you to do. However, at different pressures, okay, 5 bar, 10 bar, 50 bar, etc. So as of now, just an example, I took a 40 bar. Okay. So is sensitivity analysis clear? How did we do the sensitivity analysis? Is it clear for everyone? See, if you do with your hand, then the questions come out naturally. Okay. So next class, it will be good if you can join the session as with Aspen. That will be really great. Okay. Anyone else? Could you follow what I did with sensitivity analysis? Only two others. Thanks for your responses, by the way. And then let me show you design spec as well. Okay. For others who didn't solve that question. So design spec is available in flow sheeting options. Okay. Once you just close this design spec, I want a new one. Okay. So I'll define M7. So what I'm targeting is I want the flow rate of stream 7 to be 70%. Okay. Will flow. Okay. So I'll say M7, fix this to be 70%. I'm okay with having tolerance of 0.001. And what to vary? You vary inlet temperature, right? So since it's a temperature, so it's a stream variable. Stream 5 is what we are looking for. Sorry, it's the temperature vary from 90 Kelvin to 150 Kelvin. Since I don't know at what location it falls, that's all done. You will be able to see that it says the required input is complete. Let's run this. See, the design spec has already found a solution. It says when my inlet temperature is 109 Kelvin, 109.58 Kelvin, I'm able to get approx 0.7. So it's within the tolerance which I have mentioned to the problem. So that is what design spec does. So it's like a control loop. Okay. A feedback control system, whatever you study in your process control course, based on the output, it will give it will manipulate the input variable. So it's like having a control loop on the top of your system. So that's what design spec does. Okay. So is everything clear with respect to design spec? How did we vary input variable to match our output? Will you be able to solve in future? Can anyone respond? How is were you able to follow? Others? Only two of you are responding. Others, could you follow? Okay, fine. That's great. Let us continue. So this is what I did last week. Okay, we just started with. So what I thought actually doing is simulating the liquefaction cycle. Okay. So yes. So this is what we'll get started. We may not be able to finish it completely today, but how many of you have Aspen now, except Akshay? Only Akshay has Aspen with him, or anyone else who have joined late? Do you have Aspen except Akshay? Okay, one more has. Okay, great. So three of you have, right? That's great. We'll start with it. Okay. See, the liquefaction process. Before sending it to distillation column, we need to bring it to two phase. Okay. Uh, for the components which have boiling point close to ambient temperature and all, it's a bit easy to have them in two phase. However, when we talk of air separation plant, the major components are nitrogen, oxygen, argon, right? So they have boiling points between 77 Kelvin to 96 Kelvin. Okay, so we need to bring down the temperature to much lower temperatures from 300 Kelvin to of about 90 Kelvin before sending it to distillation column, so that we have the entire thing in two-phase system. Okay, so for that, various kinds of refrigeration processes are used. So one such process is shown over here. Okay, so this is called Kapitsa process. So what is done is air is compressed and send it to after cooler. Then we have set of heat exchangers from where from between the heat exchangers a part of compressed air is expanded to a lower pressure using a turbine. Okay, so this causes reduction in temperature, which is used to cool the incoming high pressure air. And finally the cooled high pressure air is expanded in cryoturbine and then to a phase separator. Okay, so whatever we have, the liquid product is sent to the distillation column. Okay, so this is what is normally done in any air separation plant. So I want you to set up a flow sheet which is shown inside this red box. Just leave about the compressor and aftercooler for now. So just set up this flow sheet. So what it says is it has got two heat exchangers. Use the multi-stream heat exchangers for simulating these two heat exchangers. I'll tell you the reason why you have to use multi-stream heat exchangers, because when we have components which have variation of Cp with respect to temperature very significantly in a heat exchanger, then there is an always possibility of having internal temperature pinches. Okay, so in that case, if you use multi-stream heat exchangers, this internal temperature pinches can be taken care. Okay, so since the Cp of nitrogen or air varies very significantly with respect to temperature, so it is advised to use multi-stream heat exchanger. Okay, so now can you please set it up? So I have one heat exchanger, a second heat exchanger, and then from middle I have expander. Okay, and on the cold side I have another cryoturbine. So this cryoturbine, whatever we have used in the previous question, the same thing can be used. Okay, we have simulated this part. Okay, now I want you to simulate this section. So two heat exchangers and one expander and one separator. Okay, to separate 4 into 4 and 4b. So all we are trying to add is 4 more model pellets to the existing flow sheet. That's all. So I hope that you guys have started working on it. Okay. Others, you can just take a screenshot of this and try working on this problem in your weekdays or whenever you have access to Aspen, and we'll finish this problem coming week. Okay, we won't be doing it today. uh, if three of you are able to finish it off, then we'll obviously finish it today itself, but it will take some time, I understand that. Others, do you have any other question which you want me to answer? Is there any concept you want me to explain? So in last couple of classes, people have asked me to explain residual curves. So I'll take up this topic towards the end of the Aspen course. Okay, maybe we have 12 classes, right? So 11th and 12th I will discuss on this topic. So do you want me to explain any other topic specifically in chemical engineering related to Aspen? Or do you have any other question which you want me to answer now? If you have any such, just put it on the chat box. Okay, if you are not responding, by default I'll assume that everything is clear to you. Okay, so please to respond. With respect to final examination, I'm not sure. Okay. I'll have to ask professor regarding examination. Whatever has been told in my domain is to give the assignments and not your regular assignments, whatever I'm discussing over here, and discuss on your doubts. The installation process or the assignment preparation process, which are uploaded in online, and the examination things and are taken care by different people. So uh, I can't comment on the final examination. Okay. Any other question do you have? But I can convey this question to the concerned person. That I can. I'll let you know this. I'll just ask regarding this. So Akshay, just can you tell me your status? I'm assuming 3 of you are doing, right? 4 all are doing. Okay, so I'm just getting confused. There are a lot of lists are in essence, so I don't know to which question this is referring to. So all of you took a screenshot of this question so that you can try it out. Meanwhile, I'll just go through this week assignment. People were asking some hints, right? I'll just see the question. So I want to get back to the website. That's why I'm asking you. If you had already taken a screenshot, then I can change my screen. Okay. Just give me a second, guys. I'll open that website.